Okay, let's start. Yes. So let's continue. Last class, so let's see, where were we? Today we're going to talk about, so we are still looking at this production scheduling problem, right? And we are, so we are basing all of our analysis on the Snow White field. And what we have done so far, we have made a calculation, just of the length of the plateau, just assuming we have to choke the whales until we reach a point where we don't have any more control. We lose control of the field, and after that point, the field enters in decline. And we have done it last class, I think, and then we discussed measures to prolong the plateau. And one of these measures, I decided to take the opportunity to go inside the discussion about compression. Okay, we will see later about liquid boosting, about pumping, but for this particular case, we are talking about gas, so we have to use compression. So let's use the opportunity to dive a bit into compression. Just for the record, we have today an important guest. He's actually the creator of this course, called Professor Michael Golan, sitting there at the back. Okay, he was the one that created this course. So yeah, so we have to make a really good job today. Okay, so he will be. You won't think that this is going on the wrong direction. So we said basically we have two ways that we can make boosting, right? We said multi-phase. We take the whole well stream, untreated stream, and we pass it through a machine that can bridge. Remember, we're always talking about two curves, available and required. And if for some reason I want a rate that is to the right of the intersection, okay? Okay, so let's put our system, okay? The Snow White. We have the template. Then we have the plem, a long transportation line, and then we have the separator. Okay, and we have three branches in our example that we are looking at. We have three branches that are exactly symmetrical. And we're saying if we look at the pressure, at the wellhead pressure, that's one of the plots you have to make. And here we said let's use the Q of the well, P wellhead, the available. Let's put just here pressure. It will be something like that. And if you look, that will be PWH available. And when we look at the pressure required, calculated counter current from the separator, that curve looks like that, right? So we said if you want to produce a rate here, then I have to choke. And if I want to produce a rate here, I have to give energy to the fluid. And basically, because this is a gas field, we have to use compression. We have to use a machine called a compressor that increases the pressure of the stream, gives energy to the stream. So that's what we are going to discuss today. So for that I have given, if some of you doesn't have it, please let me know here. There are some more. You have two diagrams, thermodynamic diagrams. Yeah, one is methane. You should have one like this. And you should have the other one, which is just a zoom in. It's a zoom in of an area of the diagram that we are going to use as exactly where our process is happening. So I told you we have two ways that we can make that are available today with the available current technology. And basically one of them is to use multi-phase boosting, that we use a pump, Okay, and there are different types. I told you we have this twin screw pump, we have helicoaxial pump. This is usually for low to medium gas content. And then you go to wet gas compressors. You have a lot of gas with some liquid, then you use this option. Okay, or then you can use another approach, which is I don't want to go into multi-phase boosting technology, but basically I want to perform single phase boosting with the technology I have today. Okay, and for that, for our particular case of Snow White, and this is, you have had many guest lectures about Osgard, that basically I use the well stream. I have to separate the gas and the liquid, and then I use for the gas a compressor, and then I use for the liquid a pump, and then I just mix them. There are some, so you see here we have another element that I painted last time, a cooler. Do you remember why we had these two elements? No? Well, one thing is that compression requires a lot of energy, right? So, and that compression process is more efficient if the temperature is less at the inlet. Okay? Then another thing is that if I reduce the temperature at the inlet, then the temperature at the outlet is also reduced. Okay? And why we don't want temperature at the outlet to be very, very high? We have the pipeline has certain temperature requirements and operating temperature. Also, some other things. So remember we have, this is a gas field, so we are adding to avoid hydrate formation. So we are adding some inhibitor that we don't want it to vaporize. It has to stay on the liquid phase. And also for the performance of the compressor. Okay, it might be that compressor has some requirements of temperature due to the seals. Okay, so that's the particular example we're going to look at today. Okay, dry compression. We are going to neglect the liquid. We are going to assume that we have dry gas, but really the amount of liquid is not much, so it's a good approximation to neglect it. And if you want to see, that's in the presentations from the company, how it looks like, exactly the same that I have made by hand, that you have yourself to know how to make it. But this is a more realistic or, more detailed how the process looks like. And has some other lines that I don't want to talk about now, but just, you have the main elements. You have the cooler, you have the separator, which is called a scrubber, when we have high gas and a little bit of liquid. Then you have the two elements, compressor and pump, and then you have the cooler and the mixing point. Okay, exactly the same. And that's how, in the case of Oscar, how the modules look like. Okay. So to start with, I want all of you to look at, at this drawing, at the drawing of methane. We're going to use methane. Remember, we don't have pure components in our well stream, okay, or in our reservoir stream. We have a combination. So the diagram will be slightly different when you have a mixture. But, the methane content is high enough such that we can use pure methane as a good approximation how the fluid will behave. So let's say so I took some data here from the case of Osgard subsea compression. Can we say that the well stream temperature of the well stream is 106 Celsius? That's how hot the fluid comes at the wellhead. Then we have that we have a cooler, right? And then we have fluid leaving the cooler. So it says that the cooler can maximum or the minimum temperature it can achieve here at the outlet, it's 20 degrees Celsius. The inlet pressure at the suction of the compressor, it's 50 bar. the pressure at the outlet of the compressor or at the discharge of the compressor is 100 bar. Yeah, and I have here some other data that we can use, yeah, maybe later. Okay, so I want you first to locate that point here in the diagram. Let's locate the inlet point to the compressor, okay, on our diagram. And that diagram, it's a pressure enthalpy. So why, first, why do I want this strange, it's not PT, it's not any, it's something a bit weird, that we are not used to in petroleum engineering, that we have pressure and enthalpy. Why do we have these two strange quantities on this diagram? Well, pressure, we are talking about as a process that is boosting, okay? It's increasing pressure. So it's nice to have pressure here because you can say, well, my compressor goes from this line to this line, right? So that's one reason. The other reason, we have enthalpy, and if you remember, so anybody here remembers like something very, very old that you saw maybe, 20 years ago, something called the first law of thermodynamics for open systems? What did it say? Okay, I have an open system, right? Let's say it's a box that we have fluid coming in continuously, fluid leaving continuously. Okay, we can put these two like 1 and 2. So what can we say if we make a control volume analysis using the first law of the thermodynamics? What can we say about this? What can we write about this system? Let me just unlock your memory. So we have here something called Q. We have here something called W, right? Work and heat coming out of that system or into that system. So we can say basically that the work minus the heat minus the work is going to be equal to the mass flow coming in and out. It's you don't have any accumulation, so basically everything that comes in comes out. And that will be times the energy of stream 2 minus the energy of stream 1. Right? All of you remember that? Yeah, more or less? Okay. And that energy, I can write it as the sum of the, if you remember, we have the enthalpy, which contains the thermal energy, the internal energy, plus the pressure, plus the kinetic energy, plus the elevation, right? And then I have minus the same thing. So that's the reason why in a compressor, if we make you try to customize this expression for a compressor, in a compressor, then the compressor might release some heat right to the environment. It might feel hot when you stay close to it, but that's not the main purpose of the compressor. It's not to heat anything, it's not to cool anything. So this one, ideally, it should be equal to 0, the heat that comes out of a compressor or into a compressor, right? So you have just that the work, or that the power that's the power that you are inserting to move the shaft of the compressor, will be equal to m and we say, so let's say we can neglect all of that. Okay, the pipe dimensions and the inlet and at the outlet, they will be more or less the same size, so the velocities won't be very different at the inlet and at the outlet. So at the end, I just have that the power that the compressor needs is just the difference in enthalpy. Okay, is related to the difference in enthalpy at the outlet minus at the inlet. Okay, and that's why I like to have enthalpy in this diagram, because it tells me how much power that compressor will need for a given compression path. Okay, so let's locate that point, and you can do it together with me. Locate that point, the inlet to the compressor on this diagram. So first we have to find out the appropriate pressure line. So here we have megapascal is 10 times 10, you find bar, right? So you have 2, 3, 4, 5. So that will be 50 bar. That's the suction, right? Suction pressure. And the discharge pressure is here. So here we have P discharge, and here we have P suction. Now, if you see, there are some lines that are made for constant temperature. Okay, you have here 200, that's in Celsius. Here it says that the temperature is in Celsius. So that's for 200, 150, and so forth. So we can assume for this particular case that the temperature, that the cooler will go all the way down. Okay, that we are cooling all the way to 20 C. And 20 C, let's see, where do we have 20? So here we have 50, here we have 0, 20 will be 1, 2, this line going up here. So it will be the intersection, the first point will be the intersection between that and this line. Okay? All of you found it? Yes? We go with pressure, 50, and then we go with temperature, 20, and we find exactly that point. Now, how do we locate the other point, right? The other point we know is going to be on this line. Okay, but we don't know what will be the temperature of that point.
What's the inlet temperature?
20, right? We said the inlet temperature from the well stream is 106. And that the cooler, if it operates very efficient, everything is perfect, it will go down to 20. Okay, the outlet of the cooler, and here we have the compressor after that. Okay, and here we have T discharge, and this will be T suction and P suction. Okay, so I know I have to go to this line, but I'm not sure which temperature. Okay, so I will tell you now the most efficient way. If I had to compress, I have to give power to a fluid, take it from one pressure 1 to another pressure 2. The most efficient process that I cannot reach it, but is the ideally, theoretically, the most efficient process is isentropic, right? The entropy is the same. Okay. So ideally, the compression process, the most efficient compression process, is isentropic. Okay, that means that S is constant. So, and we are lucky also, that's some of the other reasons why I decide to use this diagram, is that these lines, if you now look at the lines that go on this direction, they are actually lines of isoenthalpy, isoentropy. Okay, S is the same all along this line. So if you say, if I do it very efficient, ideally I found the most efficient compression process, I will follow this line and will reach here. Okay, so that will be my ideal compression process from 1 to 2.
Outlet temperature for compressor, how much it was?
Yeah, so what is the outlet temperature in that case of the isentropic? If I was able, we are not able, but if I was able to compress ideally, what will be the temperature at the outlet of the compressor? 70, yeah, like 70, maybe 5, something like that, okay? 75. If isentropic, then the temperature of the discharge will be around maybe 75. Okay. Now, what will be the real compression process? We know that's the ideal. That's the best I can get. Okay. So what will be the ideal compression process? So now let me ask you if you have been paying attention. So how, for the isentropic process, how do I calculate the power that that compressor will need? Okay, the change in enthalpy. So we come here, let's put here an S on this number 2. So we go power, let's put here an S below, saying that is the isentropic power, will be just the mass flow times H2S minus H1. Okay, and how much is that? So H2S is so it's like maybe 50, right? If I take this one down, it's around 50, right? Or maybe 40 something. Let's say 50. And the enthalpy of 1 that will be 50, 75, maybe 60 something, right? Let's say around 60 minus 65. Okay, and what about the mass flow? Okay, that's constant, but what value do we use for the mass flow? If you remember what our flow rate of Snow White, how much was it? 20. It was 20 million. Okay, and so how do we find, that's the rate, sorry, the rate of the field. So how do we find the mass flow? It's just the rate of the field, right, times the density at standard conditions. Okay, so how much is that, the density of, we are saying methane, right, at standard conditions?
Kind of 38.
38. Everybody, somebody that can make.
Yeah, 38.
I think it's like 68, no?
Depend on the condition.
Yeah, let's say Norwegian standard conditions. Okay, PSC 1.01325 bar and T 15.56 C. Okay, so I think that's around 0.68 kilogram per cubic meter. So if I make that, how much do I get? Remember, I have to change this and make, we don't have much space. Okay, so I have 20 e to the 6 times the density, 0.68. Okay, and then I have to, that will be give me in kilogram per day, and I have to transform it in kilogram per second, okay, to be able to multiply times the enthalpy, such that I will get watt, right? Watts. So I have to change that to days to seconds. How much is that? I have to divide by 24 times 3600. Yes. I get 157 kilogram per second, and then I can get my power, the isentropic power, which is 157 times 215, sorry, 115. Okay, and how much do we get? Uh, 18101 kilowatts. Okay, so that will be the compression power I need. In that case, I'm using the rate of Snow White, but this is the compression process of Oscar. They have more or less the same rate. To go from 1 and 2, I will need ideally 18 megawatts. Okay, I need a machine of 18 megawatts ideally. So now, that's the ideal case. What will be the real compression process? Do you think that point will be to the right? I have to be at the same pressure, right? I have to be at the same 100 bar. Will the real point will be to the right or to the left? The temperature will be higher than the isentropic or lower than the isentropic? Huh? Higher. Why higher?
This is not an ideal case. You have frigid and
Yeah, but why the temperature increases? Yes?
entropy increases.
The entropy first always increases, right? That's one thing. And the other thing, if you can think of, that process is less efficient. Okay, so not all the energy goes into increasing pressure. Part of the energy goes into increasing temperature. That is something that we don't want. It's just a byproduct. Okay, so for these two reasons, my compression process actually looks something more like, I'm going to put it in blue, my real compression process will look something like that. So that compression process, it's a bit, I will try to say, to know exactly the line, right, to know exactly the trajectory, we have to go inside the machine and we have to see exactly what is happening with the fluid in every step. But so that's a bit complicated process. So what we do actually, we say, well, I'm going to approximate that line with something called a polytropic process. Okay, if you remember, what is the definition of the polytropic process? So approximate the real compression process with a polytropic compression. And what does it say what does it say the polytropic expression? It says that P times V to the power of N is a constant. And by changing the number, the N, I can change actually how the line is, if I will have a higher temperature or if we'll have a lower temperature. Okay, if you remember, when N equal K, K being the ratio of the specific heat, right, Cp divided by Cv, then this process is isentropic. Yes? I hope you're kind of, that was, you thought you have to use that knowledge again, but now I'm forcing you to use it again. So I hope it's not causing any short circuit in your brain. Okay, so that's the way. And actually, it will depend, but that number, for example, for methane, it's 1.3. So I need a number higher than that to be deviating from the isentropic path. Okay, now we are going to make a zoom. Okay, and now you go to this diagram. Now we are going to look exactly at this area, right, where you have the two, the red and the blue line. And I have made already the homework for you. I tried to make a zoom, and I put here in red this polytropic process for the Oscar compressor. Okay, this red line is saying the evolution from 20 degrees C and 50 bar all the way to 100 bar. And what is the temperature we have at the end? 92. Okay. So let's put here for a real compression, for a real compression process, the output temperature and the expression is T2 over T1 equal to Rp, which is just Rp is just the pressure 2 divided by the pressure 1 to the power of n minus 1 divided by n. Okay, so that tells you that's just derived. I'm not going to make the derivation here, but that's just for a polytropic process. That's how I can predict the outlet temperature. Okay, the outlet temperature will be just the inlet temperature multiplied by the pressure ratio to the power of this polytropic. Just be careful, this is the polytropic exponent, okay? And remember this temperature, what units does it need to have? Absolute. Okay, that means either in Kelvin or in Rankine. Okay, but you have to use absolute temperature here. Okay, so that's how I made the homework for you. I think for the plot, let's put here for the plot. The polytropic exponent it's let's see if I find it here. Okay, it's 1.46. And that exponent in a compression process, real compression process, I can relate it to some sort of a polytropic efficiency of the machine. Okay, it's how, because it's not only enough that I say, well, 1.46, but I have to relate that to give me an indication of how efficient the machine is. Okay, how efficient it is to compress from 1 to 2. So the way to do it, I can just define, and that also I can do some derivations, but I can say that that's related to the polytropic efficiency by, is not an n, is the Greek letter eta, and it's equal to k minus 1 over k n over n minus 1. And for our particular case, that n efficiency, polytropic efficiency is 0.73. Okay, and that I can show you where I got it from, but basically it's kind of an old presentation from Statoil where they're making testing, and they put that number. You have here that drop efficiency measure value, okay, for one when they were doing the experimental campaign for Oscar. Okay, so I'm just taking that value, but you can use actually, any value that comes from the manufacturer. Okay, now let's go back to that figure that you have to see also some other interesting things. So what are the points, the points that I have in between? I have here, that's the inlet, okay, that's the inlet to the compressor, and that's the outlet of the compressor, okay, the discharge and the suction. So what are all of these intermediate points I have in between? Stages. Those are the stages, right? Like you saw last class, so let me pull that image. Okay, we cannot make all the compression stage, in one go. Why not? Just with one impeller, one diffuser? because it will be extremely non-efficient, right? I have to breach a huge delta P, and then that process will be very inefficient. So I prefer to split into stages. Each one will take a small pressure increase, but in that case, I can make it much more efficient. Okay, so in that case, this particular case, this compressor has 7 stages. Okay, and that's the suction to the first stage, the discharge to the first stage. Then you go, that will be the suction of the second stage and the discharge of the and we assume, that's an assumption to model this process, then that the polytropic efficiency of the stage, or the polytropic exponent of the stage, both are equivalent. It's equal to the polytropic efficiency of the whole compressor, such that they will fall exactly in the same line. Okay, if they had different efficiencies, then you will have, it will be a mess. You will have a line like that, then maybe the other stage is less efficient, then the other one is more efficient, and so forth. But we are assuming, and that's assumption that is typically made when you model compressors, that all of them have the same efficiency and they fall in the same line. I also want to make a small observations. What do you see about the power that each stage delivers in this compressor? What's the power that one stage delivers to the fluid? Right? We said that the power is just the difference in enthalpy. Yes? So the power of this stage will be that enthalpy minus this enthalpy. The power of this will be the difference, and so forth. So what can you say about the power that every stage delivers? Is it the same or not? It's not the same, right? The last stages, they deliver more power to the fluid than the first stages. Okay, and why is that? We have another assumption that we say the pressure ratio of every stage is the same, is constant. Okay, and that's also another consideration we make in compressor, is a constant for each stage. Okay, so I ask you, how do we calculate if we have the total pressure ratio of the machine and we have the number of stages? How do we calculate the pressure ratio of each stage? Let's say P outlet, right, or P discharge divided by, so we can call this P suction, P discharge. Then we have here P1, the exit of stage 1, 2, 3, 4, 5, 6. Okay, so that divided by P6 should be times P6 divided by P5 times P5 divided by P4. Okay, and so forth. So at the end we have all the stages, all the pressure ratio of every stage multiplied, right? How many times? N times, right? The number of stages. N is the number of stages. So we have the pressure ratio of every stage to the power of N, okay, not the polytropic, but the number of stages. That will be equal to the RP of the compressor, of the total compressor. Okay, so to find the pressure ratio of every stage, you just have to take the nth root of the RP of the compressor. Okay. Now, before we go and take a break, so how, just to give you a small, how does actually the process looks like in this line? I know I'm approximating with a polytropic process, right? But how does it look like in, when I plot the actual passage in every, let's say we have an impeller, the fluid comes on this side, then you have some structure that takes it to the next impeller. Okay, and then you have another structure or another passage that takes it to the next stage. Okay, so how will it look like the real process? Just just to close, to go to a break. Can I say something about, so this process from 1 to 2, okay? From in the rotor, remember we have two components. We have the rotor, the rotating part, and then we have the diffuser, in which we recover pressure, okay? Rotor, we accelerate the fluid, we provide kinetic energy, and then in the diffuser, we recover that energy. We transform that energy into pressure. So how will it look like on the diagram? When we give power or we give energy to the fluid, basically I will have a line that will look something like that. The enthalpy will increase and I will have some pressure increase. Okay, but that's not the main purpose of the rotor. The purpose of the rotor is just to give energy, kinetic energy, but the pressure will increase a bit. Okay, and then after, in the diffuser, that nothing is moving, you just have the conversion from that energy from kinetic energy to pressure. Okay, I deaccelerate the fluid. Okay, because in the diffuser, if we look at the diffuser in a very simple way like that, okay, from 2 to 3, remember I have, according to the same first law of thermodynamics, okay, I have in the diffuser, it's not the same as the rotor. The diffuser, I have no work being done, I have no heat being done, so I just have that the enthalpy, okay, and the kinetic energy. So what I'm doing here is that number 2 will have very high kinetic energy and very low enthalpy, and number 3 will be its velocity will be reduced such that the enthalpy will increase. Okay, you will have a balance, and the enthalpy of 3 will increase. Okay, and I don't want to go more in detail into that, but how much pressure I increase in the rotor and in the stator, that defines a bit the shape of the machine, okay, the shapes of the blades. But I don't want to go more in detail, just that remember the process I'm approximating with a polytropic line, but in reality I have acceleration, you have a little bit of pressure increase, and then you have the diffusion where you have, the recovery of the pressure, and so forth. Okay, you have these two, that will be the rotor, and that will be the diffuser. Okay, so let's take a break, 15 minutes, and we come back with, with the rest. Okay, so why do we care? I'm giving you a very short theory on compressor, but so why do we care? What does it affect? Our field development calculations or our field production profile calculations. Okay, in contrast with the choke you can just say, I have a delta P. I just have to care for. Yep. So what I was saying is that why do we care so much about? And I'm just giving, at the end, I'm giving you I'm trying to give you a better explanation about the equations, okay, that I'm providing here. But at the end, you just have to use the equations, okay? So, but I ask you to be a smart user of the equations, okay, to understand a bit more or less where, what do they represent. And I think this graphical, even though simplistic, it's quite powerful, to visualize. But the thing I was saying is that for choke, you say I need a choke to give me this delta P for that rate. And almost always I will be able to find a choke that will provide me that. I have to care for some things, this critical flow, I have to care for this erosion, but I almost always will be able to find, a choke. But on the other side, when I'm on this side of the curve, it's not so easy, because I might say, well, I need that, but then I will need a compressor that, doesn't exist. Okay, I will need a machine that doesn't exist, or I will be constrained. I will be using some kind of unrealistic operational settings. Okay, so let's go some things here. Okay, so one thing before we leave this graph: how do we calculate the power required by the compressor, the real power? Okay, will be just the difference in polytropic head, right? Okay, so the difference that I have here is that all. So let's say power is equal to mass flow times delta HP. That will be H discharge P polytropic minus H suction polytropic. Is that correct? Is that the total power I need? That will be the power if and only if I'm able to transfer, right, all the shaft power that I'm rotating my shaft, that I have an electrical motor moving that machine, okay? All of it is transferred to the fluid with no losses, right? That will be the energy that I will need, right? Just the difference in enthalpy from this point to that point, that we didn't compare it with the other case, The other case was 115, right? The isentropic. I think I made the calculation here. 115. Okay, and now for the real case, how much am I getting? It's 60, maybe 90, so that will be 150. So that's quite a few percent more. How much percent more? Like 30% more or less. Okay. But that's only on the side of the fluid. If I was so efficient that all the energy is received by the fluid and nothing else. But actually, I will need much more energy, okay, because that process has an efficiency. I have all kind of losses, okay. I have volumetric losses inside the machine. I have friction losses with the blades. I have recirculation losses with the passages. I have that they don't go exactly like that, but I have some eddies, turbulence. So I have energy losses all along the machine. Okay, so the real compression power, actually, I have to divide by the polytropic efficiency of the machine. Okay, and I have to divide, if I want to also take into account the friction. Remember, I have an axis that is rotating. It has a lot of friction with other metallic components. I have to include the mechanical efficiency. Okay, this one, it's usually very high. Something is typical, something between 95 to 98%. However, this one, it's for this type of compressors, it's you saw the plot, but it might be something in the range of 0.6 all the way to 0.75, okay, maximum for these kind of machines. Yes.
What about the volumetric efficiency? Does the polytropic account for that?
No, not really. Let's say in our to avoid putting more to put more to confuse you more with the discussion, let's say that it's included here, okay? But you're in reality, like Juan Manuel said, you have some recirculation. You have actually some fluid goes on the outside of the rotor and goes to the intake, okay? Because you have a pressure difference, but that we are neglecting. It's more important for pumps, okay? But for now, let's neglect that part. So you have that, and we have polytropic, mechanic efficiency, and actually this delta P, I can express it as the polytropic. I can express it if I use a real gas equation. I can say that that's equal to T suction times Z average, okay, where Z average is suction discharge divided by 2 times R divided by, times R times n over n minus 1 Rp to the n minus 1 divided by n minus 1. Okay, so that's the equation. If I don't have the plot, I have the C factor calculations available. I can make that approximation to calculate the isentropic the polytropic difference of enthalpy, okay, across my machine. And that you will have to make in the next exercise. Okay, by the way, already problem 3 is published, so the exercise set is ready, and the first two, like I already showed, but the third one is tasks 1, 2, and 3. You can solve them with what we have done so far, and task 4 is basically the explanation today and a bit of tomorrow. So I suggest we put the delivery date. You don't want to be working in Posque, in Easter, I guess, no? Or you want to reduce as much as possible the work during Posque. So I will say we put as a tentative deadline on the 26th, okay, of March, just before that Monday, before of Easter, such that you can have or can study or can do other things that you have on your mind, okay, during Easter. Yes, we will try on that date. If we see that many of you have problems, we will change it. Okay, but let's put tentatively the delivery date on the 26th. Okay, so that's the delta HP. I can calculate using this expression. I just need the N. I need the C average. The R, remember, R is the universal R divided by the molecular weight of the gas. Okay, so that's so let's talk here about I'm going to call this section, okay, let's call it simplified method to estimate compressor requirements or compression requirements. Let's call it Subsea, okay, because we are focusing in particular for Subsea. Okay. Okay, so first we have to say that we have to put a limit, okay, on the limit on the required compression power. Okay, and that limit, it's a bit difficult to say. We don't have too many Subsea compressors, but that limit per unit, it's currently on the market something around actually it's the Oscar, okay, 11.5 megawatts per unit. Okay, that tells you that's the current. That might change. Maybe in a few years you read this, you see this lecture becomes obsolete, but that's the current limit. The current machine, the biggest machine they can build is 11.5. So you already see here that we need 18. That means that we need 18 megawatts. Okay, that means that we need 2 of these guys. Okay, so that's why in Oscar you have 2 trains. Okay, what other consideration do we have to make? Okay, the outlet temperature was one of the things, right? So I'm limitation Okay, in the future, just to make the you might be working in an oil company. You want to find, if, for example, a compressor that can prolong your plateau or can produce more from your field. But if sometimes if to find a compressor, you have to have already a model. Okay, you have to have already one particular model, one particular machine that you want to use, and that process might take a long time because you have to go to a compressor manufacturer, you have to go to Framo, you have to go to Aker Solutions, and you have to tell them, I want this delta P, I want this rate, I want to have this temperature, find a machine for me, and that might take a long time. So what I'm teaching you here is like some like a simplified method to see, to try to make a pre-compression design before you go to the manufacturer and you ask actually for a particular machine. Okay, there are quite a few things, and you will see that we can, just using this simplified approach, we can narrow down if it's feasible or not, what the rates that we want to compress, and what will be the duty that we require from this machine. Okay, the size, the power, etc. Okay, so we have limitation in the outlet temperature. Typically difficult to say, but so that's due basically to operating temperature of downstream pipelines. Okay, and that's typically in the range of something less than 150 degrees Celsius. Okay, or a bit lower than that. It depends a bit from field to field, but doesn't have to be high. Then you have the other consideration that the seals to preserve or to maximum operating temperature of the compressor seals. Okay, that might be around also that number. And the other thing is what I was telling you before, that if you have at the discharge of the compressor, you have here a compressor, you have here a pump, and then you mix them, and then you have here a pipe in which you have gas and you have water and condensate, okay, whatnot here. And you might have a problem later on the pipe of hydrate formation, so you want to inject inhibitor. Okay, you want to inject methanol. If the temperature is too high, for that inhibitor to be effective, let's put the inhibitor in, this color. It has to be in the phase where we have the water, right? Like you already saw from one guest lecture, the hydrate is formed by the presence of water. So the inhibitor has to act on the water. When this temperature is too high, actually that inhibitor vaporizes and then stays on the gas phase, and then it doesn't have any effect. Okay, so that's another consideration why we want to control the temperature. And in the exercise you're going to get, or that you already got, that temperature is 150. So let's say maximum temperature to avoid vaporization of the hydrate inhibitor. Okay. Typically you saw in this MEG or TEC, or you have also methanol, okay, that are normally used. What else? Typically we have a minimum suction pressure that the compressor has to have. And that depends a bit on the model. You're going to use 15 bar for the exercise. What else? Power, temperature at the outlet, something about pressure ratio, right? We feel that there should be something there about pressure ratio, maximum delta P, something about that, right? If you have a map, okay, if you have a map, then the point has to fall inside the operational map, right? Okay. Operating point must fall on the performance map. Okay. Now, how the performance map of a compressor looks like? How does it look like? What do we put here on the? Do we have someone from process? No. Here we put pressure ratio or something indicating pressure ratio. It can also be this polytropic the polytropic enthalpy divided by G, and that I call polytropic head. Okay, this is called polytropic. But you already saw from the expression we gave before, it represents the pressure ratio. Okay, it's like another expression for pressure ratio. So don't be too concerned about that. I can have pressure ratio, or I can have that polytropic head, okay, which is nothing more than the polytropic enthalpy difference divided by the gravitational acceleration. Okay, that's 9.81. And what do I put on the x-axis? Okay, I have to have some indication of rate, right? Everything is delta P or something that gives me something related to the boosting, to the pressure difference, and I have here on the x-axis the rate, either standard conditions rate, actual rate, mass rate, something. Okay, so normally what I use here is the actual rate at compressor inlet. Okay, and how does the plot look like? Okay, you can think, in a qualitative way. If I need less rate, then I can give higher pressure difference, and if I use more rate, then I can give less pressure boost. Okay, so it has actually like the available pressure curve that we have been discussing before. It looks something like that. And these are 4 different rotational speeds. Okay, here they go increasing. Okay, if I use one rotational speed, I will be on that line, but then I use another one, then I will be on that line, and so forth. So that's the operational map of the compressor. And if my point is feasible, it will fall on top of that map. Okay, it will fall inside that area. However, I have 2 more things that I have to consider. One of them is we have a line here that we cannot go past beyond that line. Okay, if we pass, like we said on the choke, if we pass that line, means that the velocity inside the blades of the compressor is high enough such that you have, critical flow, that you are reach Mach 1. Okay, and then you cannot increase any further. So that's called the choke line. And here I have another line that I won't talk too much, that is called surge. And in surge, what happens is that the rate becomes so low that you have it stops being steady state, the flow in the compressor. You have like pulsating flow. You have flow going inside the compressor, going outside, inside, outside, like fluctuating. Okay, but if you want to read more, you go and type surge. So that map, I have given it to you on the exercise 3. Okay, if we see how the map looks like, I don't think it's pressure ratio, but I think it's okay, that's the head, and then you have the rate. Okay, and the point has to fall inside that map. Okay, clear so far? Yep. So the problem says, let's see here, what do we have? Maximum power per compressor is 11 megawatts. Inlet temperature, the minimum I can have is 20. Minimum suction pressure is 15. and the polytropic efficiency I say is 70. Okay. Now there is one small thing, and then we're almost finished with compressor. But I hope you have the energy. Are you tired or you're tired? Yeah. Can you hold like 10 more minutes? Yeah. Okay. This compression map, there is something a bit tricky. Okay, that I hope I don't confuse you. This compression map is measured. Okay, you go and you test the compressor, you measure it. Is for a given T at the inlet, T suction, a given specific gravity of the gas, okay, and for a given K. That map I measure usually manufacturers, they measure it with air, okay, and they use standard conditions, so they use 15.56 Celsius, and they use it so that those two properties are for air. Now, our compressor in our field will be operating not with air, right? We'll be operating with all kind of gases, or with gases that have different properties than air, and the inlet temperature will also change. Okay, so there is a way that I can change from this map at those particular conditions to a map for my particular conditions. So let me take a copy of that. I didn't make enough space. I can have to use a transformation for my current conditions. Okay, and it will change actually. It won't be exactly the same, but the points will be either shift a bit to the right or to the left, depending on my correction. Okay, but they will look slightly. Let's say that's my current condition, and that's the okay. So that's my test conditions. Okay, or I say my test performance conditions, and these are my current conditions. Okay, and the correction is the Q of the current. It will be equal to Q of the test times square root of K of the current divided by K of the test, square root of molecular weight of the test divided by molecular weight of the current, times, you don't have to worry, I have programmed these equations for you, current divided by T of the test, and the H, the polytropic head of the current, will be the polytropic head of the test times K current divided by K test times molecular weight of the test, T current divided by T of the test. So every point, okay, I have here, let's say I measure that for air. What's the K of the air? 1.3, and the gamma of air? Should be 1, right? Yes? Sure? Okay. And T inlet, let's say 15.56. Let's say in my real compression process, I'm taking now that compressor, I'm using it in Oscar. Okay, so now I have my T inlet is, like I say, 20 Celsius. My gamma will be methane, let's say 0.55, and the K will be now 1. I don't know, 3 something. What was it? How much did we have? Doesn't say here. 1.3. Okay, so I think it's not 1.3 for air, but it's 25 or Okay, so then I have to, all of these points, I have to shift them. I have to use that transformation, right, to find how will be now the new curve, the new compression curve. And that's where I can plot my point. Okay? Yes? Now I suggest another approach. Instead of you doing that, right, you can take the point, the operating point, and you convert it to test conditions using exactly the same approach. Because then you don't have to move all the points in the curve, you just have to move one point. And it will be exactly the same thing. Okay? So you come here to this particular point that you have, you apply, that will be, this is the number you have, that's the number you have, you calculate from Excel, and then you calculate that number at test conditions, and you plot it in the test map. And then you don't have to be changing the map. That's just my suggestion. Okay? Okay, so here I'm going to say just beware of choke line and search line. Okay, so we have quite a lot of constraints. Okay, we have the operation map is not always available. We have a minimum suction pressure we need to have. That's typically in the order of maybe 10 to 20 bar. Okay, we have maximum temperature. We have to keep it below a certain number, and we have a limit on the power. Okay, if you're working with a multi-phase booster, this usually is like 5 megawatts. That's what you have per unit. Okay, if you're talking about compressor, it's a bit higher, 11. Still, there is nothing higher in the market. And then you have the map. If the map is not available, what do we do? You work basically with an RP max, okay, and with a delta P max. Okay, RP max depends on the machine, but might be something between 3.0, and delta P, what we have today installed, is maybe 50 bar. Okay, not more than that. Okay, so I'm saying here just current limitations. Okay. Okay, in our exercise, we're going to use the map. Actually, I want to give you like the whole, that you can do it a bit more advanced. But if we didn't have the map, then we can use those approximations. We can put just a limit on the pressure ratio, and we can put a limit on the delta P. Okay, so now before we go, how are we going to tackle this exercise now that you have this knowledge? Okay, how are we going now to calculate? Let's say I want to, let me show you, that's not the solve exercise. Okay, let's read first what does the exercise say. It says you have to evaluate the use of subsea compression to maintain plateau production after natural production is reached. Yeah? So it says expand the Excel sheet to calculate provided to calculate the length of the production plateau in the compression period and compute post-plateau production profile. Okay, so now it says you have to install the compressor here, okay, at the plem. I want to put only one compressor, so that's why I decide not to put it here or here or here. I decide to put it in a common place where I can, flow from all the wells. And I want to see for how many years I can use that compressor. That's what Aker Solution proposed, okay? And you have to verify that for how many years, how many extra years of plateau that arrangement is going to give you. Okay, so before, so what do I have to make here? Okay, where did we have before our equilibrium point in our system? In the same problem, we did it last week. Where was the equilibrium point?
Compression.
No, we didn't have compressor last week. This is a new thing. It's on the choke, right? That was where we put our equilibrium point. It was here. So we basically said compute from the reservoir all the way to the wellhead, co-current. Our curve looked something like that, right? And then we compute from the separator all the way to the template. Now, can I keep the same point for the compression analysis? Should I keep the same point? No. Why not? Remember what I told you. If you have an element that you're not sure, that's the one that you're analyzing, right? If you can deliver or not. That's where you put your equilibrium point, right? So you put your equilibrium point just at the plane, upstream where the compressor station will be. And then you put the other point downstream to the compression station, okay? So that will be your new equilibrium point. Then next, what do you do after the plateau is finished? Okay, let's say here I made my calculations. I found the end of the plateau is here, 20.8, okay, after 20.8 years. And now I have to go from here, I have to make my compression analysis. Okay, so what rate do I use for that, for this analysis? This compressor, what is the purpose? It should be helping me to prolong the plateau, right? So you have to use the same rate, exactly the same. But now I have to compute the required pressure here and the available pressure here. And that will give me a negative pressure drop, right? With that delta P, what can I calculate? I can calculate the discharge temperature, right? Okay. With the discharge temperature, I can also calculate the power required of the compressor. I can calculate this polytropic head or the pressure ratio. Then I can see if the point falls inside the map or not. Yes? So that's what I want exactly you to do on this exercise. Okay? Now, it's not like in the choke case, we can say, yes, we can produce it, no problem. Now we are looking more in detail if we will be able to produce that rate or not. Okay? When will I have to reduce the rate? Yep.
When you reach the compressor power of 11 megawatts.
When you will see there are multiple operational conditions, right? With one of the constraints is violated. Okay, either when I violate the outlet temperature, either when the power is exceeded, even when I go out of the compression map. Okay. So I'm going to give just a very short, I will start to solve it tomorrow. Okay, so you have a good starting point. But basically, let's see how the Excel sheet looks like. You calculate, you see here you have temperature of the suction. We have a cooler, so we can lower this down to 20, from 70 or 67 to 20. Pressure ratio I calculate by making the intersection. Delta P, I'm going to assume a polytropic efficiency. That's something I'm giving you. We're going to use the same as Oscar. Polytropic exponent, I calculate the discharge temperature. I calculate these two sets to calculate the set average. Remember, we need that in one equation. We need the local rate, right? To plot this plot. Here I have local rate. So I have to convert from standard conditions rate to local rate. And for that I use BG. Okay? BG, standard condition rate, then I calculate this polytropic enthalpy difference. Okay? Mass flow, you already know how to calculate. I calculate the power, and this power should be less than the maximum that I have, right? I can put maximum 2 compressors. I think it was 2, right? I think it said someplace that I can have maximum. That's what they have proposed, to use 2. Okay, each one 11 megawatts. And here I have the conversion from actual conditions, current condition, to test condition, to plot it on the map. Yes? And now you will see when we go progress in different years, what will happen with the pressure ratio. It will increase, right? Because the two curves, the intersection, if I have these two, this one will be reduced and reduced, and I want to produce the rate, so it will be every time the difference with this curve, right? Sorry, it should be this. Okay, is the difference between the required. So that will be for year 1. That will be for year 2. That will be for year 3. Okay, so that will increase with time. That means that I will need more power. That means maybe for one of these years, I won't be able to compress, to provide that delta P, to provide that output. Clear? Yeah? Okay, so I'm going just to make, I think maybe 1 or 2 lines tomorrow. Okay, I'm going to give you some suggestions how we can bring the point back inside. The last thing we want to make is to reduce the rate. That will be our last option. But if we can do some other things to move the point inside, I'm going to give you some ideas on that. We can use the cooler. The cooler reduces the temperature, then I need less power. Okay, I can use, you will see for initial times, this RP will be very small, so it will fall below the map. Okay, it will be very small here, the RP. So I want to move it inside the map. For that I can use a choke. I can choke at the inlet of the compressor. Okay, so we have some tricks that we can use before changing the rate to move the point back inside the operational map. Okay, so any question before we close? No? Okay, it was a bit intense, but just to give you a feeling about compressor, what is important to consider, and you will have an exercise to practice that. Okay? See you tomorrow.